Good evening, everyone. Welcome to week 10 for the problem solving session for the NPTEL course Computational Fluid Dynamics by Professor Sreenivas Jayanti. And we'll move on to today's session. Now we'll move on to the problems. The first 5 problems are from the practice problems given in week 10 and followed by the assignment problems for week 10. So now we'll move on to the session. So in this week, it was about the numerical techniques available to solve the CFD problems that from the CFD problems from we have applied few techniques and we have arrived at the equations in the form of AX is equal to B. So this week's the main focus was about solving the given obtained equations in the form of AX is equal to B also. So by various techniques were discussed like direct and indirect approaches or iterative approaches, and the following questions are mostly are from those problems. So now we'll start the session. This is question 1. In question 1, it is asked that which of the following statements is true about alternating direction implicit scheme? Options given are it is an iterative method. Second one, it requires diagonal dominance for convergence. Third, it can be applied to three-dimensional problems. So the question is about which of the following statements is true about alternating direction implicit scheme. So we know that yeah. So basically we know when we are dealing with the alternative direction scheme, we know that it is an iterative procedure and it requires diagonal dominance and it can be applied to three dimensions. All the three statements are correct actually. Because what we are doing is we just split the given equation into two matrices form, so it would be like one is completely implicit and the other one we would solve directly. So based on this, since it is involving iteration also, it is an iterative method and diagonal dominance is required for the convergence because without that we could not form the required matrix conditions, and it can be applied to three-dimensional problems. This is also true. So we'll just see the options given are 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3. Since we know that all the three statements are correct, the correct answer to this problem is option D. We'll just see how this is. I mean, how in the sense we'll just have a few small recollection of the alternative direction implicit scheme. In numerical linear algebra, the alternating direction implicit method is an iterative method used to solve matrix equations. It takes advantage of the goodness of tridiagonal matrix algorithm. Basically, we know how to deal with the tridiagonal matrix algorithm. So this kind of splits the matrices into two. So in the by taking the advantage like similarity from the tridiagonal matrix approach. So this one is an iterative technique. So this scheme is expected to be faster than Gauss-Seidel method, but not as fast as the optimal SOR method. So if we take the form Ax is equal to B, we decompose it into A is equal to A1 plus A2. And then we can put it in this particular form: 1 plus tau 1 A1 xn plus half is equal to 1 minus tau 1 A2 xn plus tau 1 B. And here we can see that this one is at n plus half time step, and this is at nth time step. And this is in order to get, like, we need to move from n to n plus 1th time step, right? So in between that we have one more half, n plus half the time step, and then we move on to the nth time, n plus 1th time step. So basically, like, this one is an implicit one, this one is an explicit one. So this method we go by step, and therefore at finally we obtain the solutions. It forms a tridiagonal matrix approach. So it takes advantage of the goodness of the tridiagonal matrix algorithm, and it is an iterative technique. Yeah, so from this we can see that it is an iterative technique, and so since it is diagonal dominance is for convergence is required, it can be applied to three-dimensional problems also. Now we'll move on to question 2. For the solution Ax is equal to B, which of the following decompositions of the matrix A is the most implicit? LU, ILU, LU plus N as in SIP, LU plus N as in SIP. Okay. So the question is, which of the following is most implicit one? LU decomposition, we know that it is a direct method. Like, we'll get the solution directly from this. So it is the most implicit method, because in ILU method it is not evaluated completely and requires iteration. And ILU is incomplete LU decomposition, and in Stone actually proposed an ILU decomposition that is more implicit than ILU, conventional ILU, but it is not as implicit as LU decomposition. So the answer to this problem is first option A, that is LU decomposition is the most implicit method. So we'll move on to question 3. In question 3 it is asked that if n is the number of grid points on the finest grid, then the number of floating point operations required to achieve a given given level of convergence in the multigrid method varies as n, approximately n to the power of p, where the value of p is. So in this question it is asked that if n is the number of grid points on the finest grid, then the number of floating point operations required to achieve a given level of convergence in the multigrid method varies as n to the power of p, that is where n is the number of grid points. And the question is about the value, how is the value of p. We know that for different methods we have different n to the power of p. For example, in multigrid we approximately it is n power 1.05, and for Gauss elimination it is n power 3, and Gauss Seidel it is n square, and optimal SOR it is approximately 1.5, and so on. So 1.25 it comes for conjugate gradient scheme. So the answer to this problem is 1.05, where n is n to the power of p, where p is about 1.05 for the multigrid approach. We'll move on to question 4. In question 4 it is about just a minute. Question 4 Advanced iterative techniques are used primarily to enhance which of the following aspects of the basic iterative methods: convergence conditions, convergence rate, ease of computation. We saw how advanced iterative techniques are used in the lecture series. So basically what it does is that it enhances the computing convergence rate or convergence condition, so that it is easier to obtain convergence in limited time or with ease in obtaining that. But the procedure involved in advanced iterative techniques are rather complicated. It is not easier at all. So basically, so the following aspects of basic iterative methods are used to enhance, which of the following are enhanced in advanced iterative techniques are: convergence condition is enhanced, convergence rate is enhanced, but ease of computation is not enhanced, rather it is becoming much more complicated. The main focus here is to obtain faster convergence with different conditions, because we cannot expect the problem to go on for a long period of time and get the results. Rather, we require the faster results. So the iterative techniques are primarily involved in such a way that they enhance the convergence rate and the convergence condition. Rather, the computation becomes complicated. To say it becomes complicated rather than it becomes easier. So the answer is options given are 1 and 2 and 2 and 3, and it is 1 and 3 or 1, 2 and 3. We know it to be 1 and 2. So the answer to the fourth problem is option A, that is 1 and 2. Now we will move on to question 5. Which of the following statements is true about the multigrid method for solving Ax is equal to B? Uh, Basically it uses multiple grids for the same domain. It uses multiple grids for the same equation. It solves the same equation on all grids. We know that what we do in multigrid method is that we take a certain system and we solve the same we solve the equations for different grids. Like we'll start with the finest grid and we reduce the we get one error and we coarsen the mesh and we get the error to be reduced. This process is repeated, like the grids are varying, and so the our answer is like it uses multiple grids for the same domain and it uses multiple grids for the same equation. Like same equations, we use the multiple grids. Like for example, we start with the finer mesh and then move on to coarser mesh, and further move on to coarsest mesh. Like so finally we get the reduced error, and this reduced error we put it back in the finest grids, and then we solve for it. So like for example, here it is given actually. um, we'll just have a look, because following problems are also mainly focusing on multigrids method also. So we'll just have a quick glance here itself, so that it will be easier. So basically, the idea of multigrids methods is that in an iterative method, we are trying to reduce the original residue, and residual represents the degree of non-satisfaction of the current solution with respect to the original governing equation Ax is equal to B. For example, we get one solution and and that solution does not match with the solution from the original governing equation. So basically there is some residue. That is because of the error present, right? So in this method what we do is we are trying to reduce this residual. The idea of multigrid method is that in an iterative method we are trying to reduce the residual, because there is some dissatisfaction with respect to the system where the current solution does not matches with the original governing equations solution. So we are trying to reduce this error. This error can be decomposed into many components, right? So there are methods like Gauss Seidel, which are on using those methods we can reduce the error, which is at the smallest scale of error, and there are other methods which are not so very effective in reducing the error. So all errors cannot be reduced by the same techniques. So if there is for example, like large wavelength error and small wavelength error, so some techniques would be effective with some, and while some other would be not so effective in those cases. For example, here it is Gauss Seidel and all are good at reducing short wavelength errors, whereas if for higher wavelength errors these are not so effective. Like we need a grid space to be larger in such cases, so this method would not be effective. If you are reducing using Gauss Seidel method, then part of the error which is there in the smallest wavelength get reduced very fast and efficiently, but the larger wavelength errors are not damped so easily. You will have to work on it many times before you can damp it. So what we how it is explained is that the main motto of CFD is to get the solution in a particular domain, right? For that particular domain we would be having a certain governing equations, and we are trying to simplify it and solve it using some computational techniques. So basically residual would be there, which is the difference between the original solution of the governing equation and the solution that we are getting. So this residual is because of the error, and the main motto is to reduce this residual. So this error can be of various components like short wavelength error and large wavelength errors. So all the methods are not good at solving all the errors. For example, Gauss-Seidel method, here it is given that they are very good at solving short wavelength errors. So if there is some system component, error in the system, which is because of the short wavelengths, they would be reduced very fast and efficiently. But if there are larger wavelength errors, they would not be damped so fast when we are using Gauss-Seidel technique. So we have to work on it many times to reduce that error. So in order to have an efficient way of solving this problem, we go for the multigrid method. In multigrid method, we start with the computation on the fine grid. We do a fewer number of iterations, and then we take the error from the fine grid to the coarse grid. There we work some more iterations, and because it is now coarser grid, what were earlier long wavelengths, some of them would be damped out quickly, and then we go to the next even coarser grid, so that the middle coarser grid is unable to damp out quickly. This will be damped out in the coarser grid. So basically we will start with the smallest grids. So in this grids, the shorter wavelength errors would be removed, and then we move on to the next next coarse grid. In that coarse grid, the somewhat longer wavelengths error would be reduced, and further we would move on to the coarsest grid, where we would dampen out further largest wavelength error, longest wavelength errors. So in this step by step manner we would be reducing the error, so the error will be damped out. in each grid you are doing only few iterations, and then you go to the courses grid, and now you have reduced the error. This, and we would have reduced this error, right? And then we would use this reduced error to improve the solution on the fine grids, and then further the calculation continues. So the error from the courses to grid is used to in the finest grid, and then the calculation is done further. So this system given here, like the question given is asking about which of the following statements is true about the multigrid method for solving Ax is equal to b. First one, it is given that it uses multiple grid for the same domain, and second option, it uses multiple grids for the same equations. It solves the same equation on all grids. So, and actually this domain, it is same, that is in the domain it would be solving the same equation, but not on all the grids it is not solving the same equation. So it uses multiple grids for the same domain, and also it uses multiple grids for the same equation. So both these are true, so the answer is 1 and 2. So the correct answer is option E, that is 1 and 2. It uses multiple grids for the same domain, it uses multiple grids for the same equation. I hope this is clear. Okay. Yeah. In numerical analysis, multigrid method is an algorithm for solving differential equations using a hierarchy of discretizations. They are very useful useful in problems exhibiting multiple scales of behavior. For example, many basic relaxation methods exhibit different rates of convergence for short and long wavelengths components, suggesting these different scales be treated differently. The main idea of multigrid is to accelerate the convergence of a basic iterative method, which generally reduces the shorter wavelength by a global correction of fine grid solution approximation from time to time, accomplished by solving a coarser problem. So basically, it is accelerate the convergence rate in the basic iterative problems. From time to time, thereby we are solving the problem. The coarse problem, coarser grid, it would be easier to solve, right? While the coarse problem, which while cheaper to solve, is similar to the fine grid problem in that it also has short and long wavelength errors. It can be solved by a combination of relaxation and uphill to still coarser grids. So this is what was explained in the previous slide. Like we are moving from a small finer grid to the coarser grid, and thereby we are solving the equations and getting the errors or dampening the errors, and using the dampened error in the again in the finest grid, and moving further for the calculations. So these are all the practice problems given in the week 10 problems. So now we'll move on to the assignment problems, that is the original assignment problems, and we'll solve the session. So yeah, just a minute. Just read out this assignment statement, and we'll start solving it in a minute. So this is the assignment problem for Big 10. So in this it is asked that you wish to solve the Poisson equation in a two-dimensional domain shown in figure 10.1, that is this one, A, B, C, D. The rectangular domain EFGH has a constant source per unit area. So basically this has constant source. Side AD has Newman boundary condition. While AB, BC, CD are Dirichlet. So this one is Dirichlet. Again this one is Dirichlet boundary condition. Again this one is Dirichlet boundary condition. You use uniform mesh and use a second order accurate discretization of the Poisson equation. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Px is equal to Q. For this problem, answer the following questions. So basically, you wish to solve the Poisson equation. We are solving the Poisson equation in this domain, two-dimensional domain. With inside is a rectangular domain EFGH which has a constant source per unit area. So this side AD has Newman boundary condition. So what is Newman boundary condition? It is that we have a flex value given in that domain. Or we have the value for the differential form or the derivative form in that side AD, whereas in AB, BC and CD we have direct values given for the system. That's why we have Dirichlet boundary conditions in those three sides. We are using a uniform mesh and second order accurate discretization of the Poisson equation. You wish to solve the resulting set of linear algebraic equations. So we are expressing the resulting set in the form Px is equal to Q. For this, answer the following questions. So now we will solve this problem. Basically, we are solving Poisson equation, right? So Poisson equation in the 2D form is given by this equation: dou square f by dou x square plus dou square f by dou y square is equal to some c, that is x comma y. If it is a Laplace equation, we would be getting a 0. Since it is a Poisson equations, we are getting a c, which is a function of x and y. So we are discretizing using second order scheme. Second order accurate discretization of the Poisson equation. So we are using central difference scheme. It is fi minus 1j minus 2 fi comma j, that is we are having j plus 1 and 1 more. So if it is j, this one will be j plus 1. Sorry, this is j and this is j minus 1. And similarly, this is I plus 1 and this is I minus 1. So this one is this point. So I j minus 1, and we will be using these many points for the central difference scheme of the second order equations. So fi minus 1j and fij, for evaluation of this point we are using these many 4 other points. So this is the discretized form: fi minus 1j, fi comma j, fi plus 1j. This we are at with respect to the x, with respect to the x1, and fij minus 1, fij plus 1. This is for respect to y term, and it is constant, not constant, some variable. This is the Poisson equation discretized in the two-dimensional form. So yeah, we now move on to the questions. Which of the following methods can be used to solve the Px is equal to Q from the above problem? ADA, that is alternating direction scheme, and ILU method, that is incomplete LU decomposition method, and the TDMA method. So actually, if we could remember in the last lecture itself, we have discretized this equation, and we were able to see that we could not able to get the tridiagonal matrix in that. Rather, we were getting some other elements also in that system, some other non-zero elements also. So we can use ADA method and ILU method, but tridiagonal matrix algorithm cannot be used because it was not forming in that structure. Like I hope you could remember from the last lecture, I mean last problem solving session, this is not, we were not getting the tridiagonal matrix. So the answer is 1 and 2. 1 and 2 is right. 1 and 3, third statement is wrong, and similarly third statement is wrong. And so yeah, answer is option A. That is alternating direction implicit method, and that incomplete LU decomposition method can be used, whereas PDMA cannot be used. Which of the following methods can be used to solve the Px is equal to from the above problem? PDA and ILU method can be used, TDMA cannot be used. Now we'll move on to question 2. Which of the following methods cannot be used to solve Px is equal to Q from the above problem? Just a minute, guys. Which of the following methods cannot be used to solve the Px is equal to Q? The first one is SOR method, that is successive over relaxation method, and multigrid method, and SIP method, that is Stone's incomplete LU decomposition method. So basically we can use all these methods to solve the above given problem in the form of Px is equal to Q. There is no criteria that is not being solved. All these are direct techniques. So like SOR we should give over relaxation factor, and multigrid it is solving this equation in multiple grids, and this is a LU decomposition method in an with some modifications. So all these methods can be used. The given options like 1, 2, 3, all of them are wrong. Like they can be used. Since the question is about it cannot be used to solve this problem, answer is option D, that is all the three can be used to solve this Px is equal to Q format. In question 3, it is asked that which of the following statements is true about the source term in the region EFGH? It strengthens the diagonal dominance of the discretized equation in the region. It weakens the diagonal dominance of the discretized equation in the region. It affects the column vector Q. If you can remember, we are discretizing it using 4 points. I mean 4 points are considered for every equations, right? And we are using it as Px is equal to, and in the previous slide itself we saw the Poisson equation, dou square f by dou x square plus dou square f by dou y square is equal to some variable. In this is the discretized format. This is the source term, right? In the EFGH, it is given that we have a constant source per unit area. Therefore, this one remains a constant in the EFGH. Constant source for EFGH. That is, we are having one big domain. Inside one, we are having a small portion EFGH, which is having constant source. Therefore, the source term generally appears, since it is a constant one, we are taking it in the Q, like it would become constant and move into the Q vector, that is the column vector. No other, like since this one is a constant, no other changes in P or Q X is observed. Therefore, it strengthens the diagonal dominance of the discretized equation in the region, that is false. Similarly, it weakens the diagonal dominance of the discretized equation in the region. We are not, this particular source term is not doing anything in favor or against the diagonal dominance of this discretized equation. Rather, this term is a constant and it is behaving rightly so as a constant by affecting only the column vector q, where the equations are in the form of px is equal to q. So the answer is option 3 is the only right option given here. So we'll see the options. A, it is 1, B, it is 2, C, it is 3, that is correct. 1 and 3, it is wrong because 1 is wrong, and similarly 2 and 3, it is also wrong because 2 is wrong. So the answer is option C. I hope this is clear. Now we'll move on to question 4. Which of the following statements is true about the site EH? Dirichlet boundary condition is applicable on EH. Newman boundary condition is applicable on EH. Robin boundary condition is applicable on EH. No boundary condition is applicable on EH. So we know that ABCD is a domain under consideration, and inside that we have a small portion EFGH, right? So the options, it is given Dirichlet, Newman and Robin. We know the Dirichlet boundary condition, where if we know the value of a specific variable, we call it Dirichlet boundary condition. If we know the value of the derivative of that particular variable, we have the Newman boundary condition. Then what is Robin boundary condition? Do any one of you know what is Robin boundary condition? It's in Robin boundary condition, it is a weighted average of Dirichlet and the Newman boundary condition. This is different from the mixed boundary condition, where in mixed boundary conditions, boundary conditions of different types are specified on different subsets of the boundary. Rather, in Robin boundary conditions, both of them are present with weighted average. Like, for example, consider a variable u. In Robin boundary conditions, we would be okay. Dirichlet boundary conditions, we would be having u is some variable, I mean some value. For example, u is 0 or u is 1, something like that. In Newman boundary conditions, we would be having it as dou u by dou x is equal to 1 or dou u by dou x is equal to some g. Whereas in Robin boundary conditions, we would be having u times of something plus dou u by dou x times of something is equal to some value. This is what is given in the Robin boundary conditions. Whereas in mixed boundary conditions, It is a separate thing. Like for example, consider some area. We will be putting Dirichlet boundary conditions till some area, and from the remaining we have the Newman boundary conditions. If it is given like that, that is mixed boundary conditions, and if weighted average of both of them are given, that is known as mixed Robin boundary condition. Uh, so now we move. Okay, given the definition, we should see what it is for the EH side. We have the side EH, so we know EFGH is a constant source per unit area. A thing to be noted is we are solving the Poisson equation in this complete domain. So since this domain has a constant source per unit area, but if we see this, we can see that it is not in the boundary, it is in the interior plane. So we won't be requiring any boundary conditions to be used in this area. So the answer is no boundary condition is applicable on EH because it is in the interior of the plane. No boundaries are present in the EH. EH may be a boundary to the small section, but since we are solving it in entire domain, we don't require the boundary condition to be applied to the side EH. Now we'll just see the question 5. In question 5, it is asked that which of the following statements is true about SOR method if the coefficient matrix is diagonally dominant. Its convergent rate increases monotonically with SOR parameter W. It is convergent if it is or W or omega is between 0 and 2. Its convergence rate is twice as much as that of Gauss-Seidel method. So what is SOR method? SOR method is successive over relaxation technique. So in this we introduced an additional term omega or W in the iterative technique like Gauss-Seidel, and this omega like increases the convergence rate in the system, but we would say it is, if it is omega is between 1 and 2, it is over relaxed, and if it is between 0 and 1, it is under relaxed. But we cannot say that its convergent rate is monotonically increasing with SOR parameter W or omega, but we can say it is convergent if it is omega is between 0 and 2. And also same way we cannot say it is twice as much as that of Gauss-Seidel. If anyone of you remember what is the convergence rate, like it is somewhat faster than Gauss Seidel, but we cannot say it is um, twice as much as Gauss Seidel, because generally the number of equations or number of grid points in the Gauss Seidel is um, n square, where n is the number of grid points, whereas in optimal SOR it would be around n power 1.5. It is not like convergence rate is not twice as much as that of Gauss Seidel. It is increased somewhat, but we do not know the exact value. So the only option that is correct in this given statement is second one. It is convergent if omega is between 0 and 2. So the answers options given are 1. 1 is wrong. Basically, it's not increasing monotonically with omega. And but 2 is right, because it is convergent if it is omega is between 0 and 2. Its convergence rate is twice as much as that of Gauss Seidel. That is also false, because it is not twice. It is more, but we cannot say it as twice. And 1 and 3 it is wrong, and similarly 2 and 3, 2 is right but 3 is wrong. So the answer to this is option B, that is second statement. It is convergent if it is between 0 and 2. So basically, as long as omega is between 0 and 2, convergence is assured in SOR. So as long as omega is between 0 and 2, convergence is assured. This is the fact with SOR, the optimal SOR. The rate of convergence is varying, which depends as before on the spectral radius of the new iteration matrix. Omega varies between 1 and 2 for case of over relaxation, but the rate of convergence does not vary monotonically between 1 and 2. Typically, it goes through a minimum or the number of iterations needed to produce a residual by a factor of 10. The value is asymptotically convergence rate. If it reduces as omega is increased, it goes to a minimum and then it starts coming back. So that means there is an optimum value of omega for a given matrix and for the given SOR. This optimum value will have the least number of iteration steps needed to reduce the residual factor by a factor of 10. For example, yeah. So what do we do in successive over relaxation method is that we introduce an additional term, omega, in the traditional iterative techniques. This omega is between, okay, sorry, this omega is between 0 and 2. If it is between 0 and 1, we call it under relaxation. Under relaxation. If this omega is between 1 and 2, we have over relaxation, successive over relaxation. This is what we are focusing over here, right? And the rate of convergence is varying, which depends on the spectral radius of the new iteration matrix. So the rate of convergence, actually it is varying because depending on the new spectral radius of the new iteration matrix. The spectral radii, new iteration matrix should be formed based on the introduced factor or introduced parameter omega. Omega varies between 1 and 2 for case of over relaxation, but we cannot say that if omega is between, as omega is going from 1 to 2, we cannot say that if it is 1, right, it is a normal iterative technique, the similar one. But if it is going from 1 to 2, we cannot say that the rate of convergence would be going from 1 to 2. That is, it is not twice as the normal technique. What happens is that as we increase omega, okay, not here, as we increase omega, the rate of convergence is there, right? It increases, and after a certain point it gets reduced. The rate of convergence is again reduced, so this point is there, right? This is the optimum SOI, optimum value of omega. At this omega there is a least number of iterations which helps in getting the reduced convergence, convergence rate at faster interval, faster time. Basically at this point the number of iteration steps required is very less, so that the iteration in the n plus 1 time step, residual at n plus 1 time step is, residual at nth time step would be like if residual should keep on decreasing, right? So it would be less than 0.1 or equal to 0.1. So this is what we do in SOR technique. Like in SOR technique we have a value between 0 and 2. Omega is varying between 0 and 2. Convergence is guaranteed actually, because if it is between 0 and 1 we have under relaxation, we have 0, 1 and 2 it is over relaxation. But for under relaxation we cannot say that as omega is increasing, convergence is increasing in the same speed. It is not so, like it does not the rate of convergence is depending on the spectral radius of the newly formed iteration matrix, and omega varies between 1 and 2. In that zone it does not, rate of convergence does not vary as monotonically between 1 and 2. Typically it goes to a minimum of the number of iterations needed to reduce the residual by a factor of 10. This value is asymptotically convergence rate. It reduces as omega is increased, it goes to a minimum and then it starts coming back up. So that means there is an optimum value of omega for a given matrix and for a given SOR method. This optimum value will have the least number of iteration steps needed to reduce the residual by a factor of 10 and have the convergence rate, highest convergence rate. So at the optimum point, that is optimum SOR, we have the omega value. At that omega value we would be having the, we would be requiring the least number of iteration steps to reduce the residual by a factor of 10. So basically the question that was asked was, which of the following statements is true about the SOR method if the coefficient matrix is diagonally dominant? In this system itself it is given that the coefficient matrix is diagonally dominant, because that is an important criteria when it is coming to SOR like technique, where we are focusing on iterative techniques. So since diagonal dominance is given, the condition is satisfied. So its convergence rate increases monotonically with SOR parameter omega. It is convergent if it is between 0 and 2. Its convergent rate is twice as much as that of Gauss-Seidel method. So basically the second one is the only statement that is correct, because it is convergent between 0 and 2. It convergence is guaranteed, because it is, if it is less than omega it is under relaxation. If it is greater than if it is less than 1 it is under relaxation. If it is greater than 1, over relaxation, and at 1 we have the normal iterative technique. But we cannot assure that the convergence rate increases monotonically with the SOR parameter omega. Similarly, we cannot assure that the convergence rate is as much fast as, twice as much as that of the Gauss-Seidel. Both of the statements are wrong. So the answer is 1, 2, 3, 1 and 3, 2 and 3. So the answer is option B, that is second statement is the only statement that is correct. So now we'll move on to question 6. Before that, if any of you have any queries in the last few problems, you can ask, or you can stop and ask me at any point of time. At whatever time you have doubt, please feel free to ask the questions. And your feedback is highly appreciated. So please feel free to give the feedbacks also. Now, just a minute. We'll just start it in a minute. So, in question 6, it is asked that in comparison with the Gauss-Seidel method, number of floating point operations required one iterative step of going from xk to xk plus 1 using the SOR method is. So, basically, like in Gauss-Seidel, the number of floating point operations required for one iterative step of going from xk to xk plus 1 using the SOR method is. When we are formulating the equations in Gauss-Seidel and the SOR technique, they both remain the same actually. With an additional parameter omega in the SOR method that decides the convergence rate. So, but basically, with omega, the method is optimized in SOR. So the rate of convergence is regulated in the SOR technique. But if you are looking for the floating point operations requiring one iterative step of going from xk to xk plus 1, the number of operations required in the performance or the number of operations required to solve that set of equation is almost remaining the same. That is, for Gauss-Seidel and Gauss SOR method, they are just the same. Like for example, Gauss-Seidel. Sorry. Okay, we'll keep it as Gauss-Seidel and SOR. So both of them have the same set of equations. Equation is the same here, whereas the equations would be influenced by factor omega. This omega would be between 1 and 2 for the over relaxation. So in previous slide itself we have seen that how with the rate of convergence actually varies for the Gauss-Seidel and the SOR, because with Gauss-Seidel the rate of convergence would be slower than the SOR technique. But if we look into the rate of convergence versus the omega plot, we have seen that it is increasing and after which it decreases. So this is the optimum value of SOR. So this omega decides the fastest rate of convergence with fewer number of iteration steps. The iteration steps would be reduced, but between a single iteration step, the number of floating point operations required would remain the same. So as you can see, the number of iteration steps would be reducing when we are going with the SOR technique, but the number of floating point operations required for one iterative step remains the same between the Gauss Seidel and the SOR method. So the answer is okay. The options given are far more, twice as many, about the same, far fewer. So it is not far more, and similarly it is not twice as many, and it is about the same actually. The number of floating point operations remains the same between Gauss Seidel and successive over relaxation technique, and far fewer. So the answer is option C. That is, it remains about the same. I hope this is clear. Now we'll move on to question 7. Okay. This is ADI method for the solution A of AX is equal to B is based on the decomposition of matrix A into M plus N. Problem into two tridiagonal matrix problems. Matrix A approximately into LU, none of the above. So in alternating direction implicit method, the main goal is to divide the if we are given the set of equations in the form of Ax is equal to B, we are modifying the A into a something like so that when we are putting it back in the equation, we would be having one explicit and one implicit term. We are not simply dividing the matrix A into M plus N with different, in those M and N are of certain things, but rather we are dividing the matrix A into two tridiagonal matrix, so that we are getting a new approach over here. So the answer is the matrix A into M plus N, this is wrong. The problem into two tridiagonal matrix problems, this is true. Matrix A approximately into LU, this is also false. We are not splitting A matrix into LU. Rather, we are going with two tridiagonal matrix problems. Option D, none of the above, is also false because option B is the correct answer. The problem is being split into two tridiagonal matrix problems. So we'll see that how. In numerical linear algebra, this slide we have seen before also, but to look into it and understanding based on the context in the question, I have put it again. So in numerical linear algebra, the alternating direction implicit method is an iterative method used to solve matrix equations. In previous question it was about this one, asking about iterative method. I guess it takes advantage of the goodness of the tridiagonal matrix algorithm. This scheme is expected to be faster than Gauss-Seidel method, but not as fast as the optimal SOR method. So it is given that this method is faster than the Gauss-Seidel, but it is not faster than the optimal SOR. It is somewhat lying between Gauss-Seidel and the optimal SOR method. So here, if the matrix is given in the form of Ax is equal to B, then we are decomposing it into A is equal to A1 plus A2. And then we can put it in this particular form, 1 plus tau 1 A1. Okay, this one is not so good. The superscript and subscript. So in alternating direction implicit method in this thing, we are dividing it into A1 and A2, where A1 and A2 are two different, two tridiagonal matrix given, so that we can see that in order to jump from nth time step to the n plus 1th time step, we are having two steps. In the first step, we are evaluating at n plus half time step, and in the second step, we are using n plus half the time step to get the n plus 1th time step. So we can see that the right hand side is explicit, whereas the left hand side is the implicit one. We are solving it simultaneously. So it can be seen that one explicit and one implicit terms are, groups are present in this equations. So what was the question again? It was ADI for the solution of Ax is equal to B is based on the decomposition of matrix A into M plus N, matrix A into two tridiagonal matrix problems, matrix A approximately into LU, and none of the above. So the answer is, by now we know that the answer to this problem is divided into two tridiagonal matrix problems. So do anyone of you remember what was the question asked about the this one in the previous one? Yeah. Okay. It is an iterative method. It requires diagonal dominance for convergence. It can be applied to three-dimensional problems. Yeah, all three statements are correct. So basically, the answer to this problem was option D, which is having all three options like 1, 2, and 3. So I think now by now you would have gotten some idea about. Okay, this one, it is seen that A2 part is being evaluated explicitly and A1 part is evaluated implicitly. So this is what I mentioned over here, that is A2 part is evaluated explicitly and A1 part is evaluated implicitly. RHS is explicit and LHS is implicit. Yeah. So we'll move on to this session, and the problem was, where were we? Okay, here also it is mentioned that A2 part is, I don't know why I didn't do anything about it. A1 part is evaluated implicitly and A2 is explicitly evaluated. This one here we can see that where's the pointer? This one is A1 and this is A2. A2 is evaluated at nth time step, so we know that. So A2 is evaluated explicitly, whereas A1 it is evaluated at n plus half time step. So we do not know that, right? So this one is evaluation implicitly. Similarly, here also A2 is known, A1 is unknown. So I hope this is clear. Now we'll just move on to next problem, that is question 8. In the SIP method, for the solution of Ax is equal to B, matrix A is decomposed into LU, ILU, LU plus N, none of the above. LU is like we are splitting the LU decomposition method, where we are splitting a matrix A into a lower triangular matrix and then upper triangular matrix. In ILU method, it is incomplete LU decomposition method. That is, here also we will be splitting. This is an improvised version of the LU decomposition method, and where we would be having it in a slightly different form or different context with a different structural, different structure matrix. For example, if consider that a matrix A, for this problem of Ax is equal to B, uh, So if we are splitting it as a LU decomposition, in LU decomposition, what we would be having is, we would be having three rows, three non-zero rows. For thing is, Ax is equal to B. In A, we are having five non-zero rows, non-zero diagonals. And in L and U, we would be having three non-zero diagonals. In this incomplete LU, we'll be having an additional like M, with 7 non-zero diagonals. So this is an somewhat a different version of decomposition of LU. So this is known as incomplete LU method. And in Stone actually proposed an advanced version of the LU decomposition, that is known as Stone incomplete LU decomposition. This Stone proposed it in 1968. Modified ILU decomposition method. This modification is given in the form of LU plus N. To be known, this LU plus known is more implicit than the conventional ILU, but LU decomposition matrix is the most implicit one over here, followed by LU plus N, which is more implicit than the ILU method, ILU matrix, ILU decomposition. So the least one is ILU decomposition, and the more implicit is ILU decomposition. The thing is that when we are dealing with explicit scheme, we are going step by step manner. So the time step matters more over there, and we should give it a very lower values to cover everything. Rather, if we are going with implicit scheme, everything values would be known at a certain thing, and every values we would be putting it, and we would be solving all the equations simultaneously to get the solutions. So it would be, the time step would be not need not be very smaller one for implicit case. Therefore the more implicit, the more faster would be the case. So these are all the methods. And actually the answer to this question is, in the SIP method, for the solution of Ax is equal to B, matrix A is decomposed into ILU, ILU, LU plus N, none of the above. So answer is option C, that is LU plus N. Stone in 1968 proposed an ILU decomposition which is more implicit than the conventional ILU. So we'll move on to question 9. Okay. The questions 9 and 10 are based on multigrid approach. So in previous slide also we have seen about the multigrid method. So we'll just put that slide also over here and have a quick recap of the multigrid methods. And proceed with the questions 9 and 10. Okay. In multigrid method, in numerical analysis, multigrid method is an algorithm for solving differential equations using a hierarchy of discretizations. Okay, this is a method where we are solving a differential equations where we have a hierarchy of discretization. That is, we solve from finest grid to the coarsest grid. They are very useful in problems exhibiting multiple scales of behavior. For example, many basic relaxation methods exhibit different rates of convergence for short and long wavelength components, suggesting these different scales be treated differently. In this, it is given that many relaxation methods exhibit different rates of convergence for shorter and long wavelength errors components, suggesting different scales be treated differently. Everything cannot be put in together in a single thing, like we need a variations for different methods. The main idea of multigrid method is to accelerate the convergence of a basic iterative method known as relaxation, which generally reduces short wavelength error by a global correction of the fine grid. Okay, the main idea of multigrid method is to accelerate the convergence of a basic iterative method. The basic iterative method is known as relaxation, which generally reduces the short wavelength errors. This main idea is to accelerate the convergence of this basic method by a global correction of the fine grid solution approximation from time to time, accomplished by solving a coarser problem. That is, we are solving a coarser problem, and from that we are getting an approximation of the error approximation, and we use it in the fine grid solution to get the proper correction. The coarse problem is easier to solve or cheaper to solve, is similar to the fine grid problem in that it also has short and long wavelength errors. It can also be solved by combination of relaxation and appeal to still lower coarser grids. It is that in coarser grid it would be easier to solve the errors, and some certain errors would be reduced in the long wavelength errors would be reduced in the coarser grids. So further we would be moving on to the coarsest grid, or in a step-by-step manner. From the coarsest grid we would be having an estimated error, and this error we would be put it in the finest grid and accomplish and then solve that and do further calculations. For example, this is that multigrid methods. The idea of multigrid methods is that in an iterative method, we are trying to reduce the residual, and the residual represents the degree of non-satisfaction of the current solution with respect to the original governing equations of Ax is equal to B format, and dissatisfaction is there because some error there in the solution. Basically, what we mean over here is that there is some sort of dissatisfaction, right? We have already seen this. This is just a quick recollection so that it would be easier for us to solve the questions 9 and 10. Basic idea is here we are trying to reduce the residual. What is residual? Residual is the difference between the original solution, for the discretized equation, and the solution that we are getting in the current iteration, the current solution. So between these current iteration and the original solution, what we are getting is known as residual. This residual should keep on decreasing so that the error is getting reduced. Since the error is always present, the idea behind the multigrid method is that to reduce the residual, we would be following certain things. This error component is present in the system, right? That would be of various components like short wavelength errors or long wavelength errors. So basic iterative techniques, in the previous slide we saw that basic iterative techniques would help in reducing the short wavelength errors. So Gauss-Seidel method, they are very good at reducing shorter wavelength errors, while the longer wavelength errors are very difficult to solve, and then it would be computationally expensive. They are not damped easily, and we would go for repetitive times and many times before damping the error. So, or there are some other methods which are not very effective in reducing the error. If we are reducing using Gauss-Seidel method, then part of the error which is there in the smallest wavelength get reduced very fast and efficiently, but the larger wavelength errors are not damped so easily. You will have to work on it many times before you can damp it. In the multigrid method, we first start the calculation in a finest grid, and then we do a few iterations or few number of iterations, and we take the error and move on to the coarser grid. In that we put this error and we solve that. Here the further long, like in the initial step, the short wavelength errors are reduced. In the next coarser grid, the next shorter wavelengths or the next longer wavelength errors are reduced. This would keep on going, like we move from finer to coarser, more coarser to coarsest. Similarly, the errors would keep on reducing from shorter wavelength errors to then it would be longer wavelength errors, and the longest wavelength errors would be reduced. This final error, we again take it back to the finest grid and do the calculations, and by the time the error would be damped out and reduce this error, and this reduced error is used to solve for the further calculations. So basically we are now left out with the calculations, and the thing is we are only doing a few number of iterations in each grid size. So basically this is what we do by we use by the term multigrid methods, where we are using different grid sizes for the solution of the same problem for the reduction of errors, so that the residual get reduced, and by factor of 10. It was given over here somewhere. You now reduce this error. Yeah. Not this one. The global correction. Yeah, it was given somewhere, right? So yeah, like the main objective is to reduce the residual. Solving hierarchy useful. We should be reducing the residual, so we are using a different grid approach, different grids. This is what we mean by denote by multigrid method. So if you have any doubts on this, please ask. If there is no doubt, I'll just move on to the problems for the multigrid methods. Okay, question 9, it is asked that which of the following statements is true about the multigrid method for solving Ax is equal to B? It uses several grids for the same computational domain. It is solving same equation on all the grids. It uses the same boundary condition on all the grids. Basically the thing is we are evolving from we are using different grids. So option 1 is right, several grids for the computational domain is used, and solves the same equation on all the grids is false, and same boundary condition is applied on all the grids. So 1 and 3 are right, second one is a wrong statement. So the answers options given are 1 and 2. It is 2 is wrong. 2 and 3 again 2 is wrong. 1 and 3 it is right. 1, 2 and 3 again 2 is wrong. Since it is present, the answer to this problem is 1 and 3. That is option C. First and third statements are right. The same question was given in the practice problem, if you can remember. Which of the following statements is true about multigrid method for solving Ax is equal to B? It uses multiple grids for the same domain. It uses multiple grids for the same equation. It solves same equations on all grids. Option 3 is the wrong one, whereas option 1 and 2 are right. So 1 and 2 are right. See, the same wrong statement is given in the in that problem too. Same equations on all the grids, it is not the case. Error is keeps on changing. So yeah, answer is it uses several grids for the same computational domain, and similarly it uses same boundary conditions on all the grids. So first and the third statements alone are right, and remaining are wrong. Basically, since second statement is present in all other options, the answer is 1 and 3, option C. I hope this is clear. Now we'll just move on to the next problem, next and the last question for this session, that is question 10. Multigrid method is efficient in solving Ax is equal to B because only part of the computations are solved on the grid. Computation on coarser grid takes lesser computation time. Computation on coarser grid takes fewer iterations to converge. Just Just a minute. Just a minute. I'll just check this once. So in question 10, it is asked that multigrid method is efficient in solving Ax is equal to B because only part of the computations are solved on the grid. Computation on coarser grids takes lesser computation time. Computation on coarser grids takes fewer iterations to converge. What we are doing in multigrid approach is that we are solving from the finest grid to the coarsest grid by taking the error input from the previous solution, right? So only part of the computations are solved on the grid is true, and it is also true that computation on coarser grid takes lesser time to computation time because since the grid sizes are larger, it would be easier to move on to the next solution. Next, I mean the solution would be easily solved or solved faster on the coarser grids. Computation on coarser grid takes fewer iterations to converge. Since we are going from finest grid to the coarsest grid, the error would be damped out soon, and so the fewer iterations to converge should be true. So all three statements given are true. So the answer is 1, 2 and 3 are right. 1 and 2 is right, 2 and 3 is right, 1 and 3 is also right, and 1, 2 and 3 is the right answer. That is option D is the right one. So multigrid method is efficient in solving Ax is equal to B because only part of the computations are solved on the grid. Computation on coarser grid takes lesser computation time, and computations on coarser grid again takes fewer iterations to converge. So all three statements given are right. So the answer to this problem is option D. So the last two problems are basically based on the multigrid approach that we have seen in the previous slides. So that's all for today's sessions. We have seen 15 problems. So if any of you have any doubts in those problems, you can feel free to ask. Yeah, that's it. Please feel free to ask the questions, and if not, we'll have a quick recap of the session before ending the session. So yeah, we'll just have a quick recap of the session. So, in this week, it was mainly focusing on the different schemes available to solve the obtained matrix in the Ax is equal to B format. So, the problems were mainly focusing on few things like alternative direction implicit scheme, where we divide the matrix into two tridiagonal matrix format and solve it in an iterative procedure. And then we also saw about implicit methods like LU decomposition and lesser implicit ones like stones incomplete procedure and ILU, that is incomplete LU decomposition method, and saw the number of grids like we also seen about the multi-grid approach, which was comparatively faster with lesser number of floating point operations at a given level of convergence. And mostly the methods in the like the studied methods were mostly based on these things, convergence for all these like LU decomposition, um, LU method, uh, like an SIP method, that Stone's procedure, and basic ones like Gauss Seidel iterative technique, and like previously it was also about Gauss elimination technique, if you could remember, and it is Gauss Seidel and successive over relaxation method and everything, and followed by Strong's implicit procedure. SIP is for Strong's implicit procedure. I remember I have said somewhere as Stone's incomplete procedure. That one is wrong. It is Strong implicit procedure. And also the main focus was also about the multi-grid method, um, with few problems on those. And mm, the main thing was about the convergence rate and convergence criteria, which would ensure that the faster convergence is achieved. Faster convergence in the sense the convergence would be faster, but again the thing is like faster convergence, but computationally it would be expensive, it would not be an easier one. And also like again we also have seen these were all the practice problems given in this session. With further, the assignment problems were looked upon, where it was about solving a Poisson equation in the given two-dimensional domain with three boundary conditions, like three Dirichlet boundary conditions on Dirichlet boundary conditions on three sides, followed by Newman boundary condition on a single side. And inside there was a small domain which was under our consideration, which had a constant source term. So we saw the Poisson equation in the two-dimensional form as this, and discretized in the second order form using central difference scheme. And the questions were about which were all the methods that could be used to solve the problems, like ADI method, ILU method, and TDMA cannot be used because in previous week's problem session we saw that TDMA was not giving an approximate solution. Rather, I mean to say, TDMA was could not be used because it was. I mean, sorry about saying as not giving solution. TDMA could not be used because the matrix was not forming a three-dimensional matrix. Rather, there were so many other elements present in the matrix structure. If you could remember from the previous, last problem solving session, and it was about which of the following methods cannot be used to solve px is equal to q. Again, all these methods can be used because there is no criteria mentioned anywhere making it not to be used. It cannot be used, so all three can be used. And EFGH is a smaller domain. It was having a constant source term, so that would be affecting only the RHS part, that is px is equal to q. Q matrix alone would be affected. Since q is a column vector, q alone would be affected. And again, which of the following is boundary condition can be used? EFGH is a smaller one, a smaller domain inside the system. If you can see, it was not falling on any boundary, therefore boundary condition need not be applied. Here one more thing we studied was about Robin boundary condition, which is about a weighted average of Dirichlet and the Newman boundary condition on the given side. So question 5, its convergent rate increases monotonically with SOR a successive over relaxation method. It was about introducing an additional parameter omega, where omega varies between 0 and 2. The convergence rate monotonically increase with omega. It is false because it is not increasing monotonically. Although the convergence rate is increased in the SOR technique, it is not increasing monotonically. So that one is a false statement. And then that's what we saw. Like also we saw the optimum value of the omega giving optimal SOR method, that is with increase in the omega value, rate of convergence also increases up to a certain point, after which it decreases. That optimum point is known as it reduces as omega is increased. Rate of actually I made a mistake when I was giving the lecture. So basically omega value, as it is increased, it increases and then it decreases and then increases. This is known as convergence rate of convergence. I am extremely sorry for giving this, but it decreases and then increases. So this point is known as minimum point or the optimum value. Previously I was mentioning it as increasing and then decreasing. No, it is decreasing. The rate of convergence decreases with increase in omega, and then afterwards it decreases. It reduces as omega is increased and it goes to a minimum, and then it starts again coming back. So it reduces as omega is increased, it goes to a minimum and then it starts coming back. So that means there is an optimum value of omega for a given matrix and for a given SOR. So this optimum value will have the least convergence of iteration steps needed to reduce the residual by a factor of 10 and have the highest convergence rate. So this was about the same. Actually, one more thing was that when we are dealing with Gauss seidel and the SOR, the number of floating point operations between two iterations remain the same. The omega only deals with the rate of convergence of the number of iterations involved. Rather, it would not be doing anything with the floating point operations. That thing needs to be considered. And in ADA, we are dividing the A matrix into two tridiagonal matrix. That was we have seen, and it was about the same. And SIP is strong implicit procedure. Two things I confused you people during the original session, that is SIP is strong implicit procedure, and the omega, that which is rate of convergence, it decreases with increase in omega and then it increases, so it goes through a minimum. Previously I would have mentioned it as maximum, so that was a wrong thing from my part, so sorry for that, for these two mistakes. So it was also about SIP method, and then finally again we have seen something about multigrid method and few questions that was followed on this. So yeah, that's all for today's session. We'll again meet in the next week at the same time. So this is week 10, two more weeks are remaining. If any of you have any doubts, you can put it in the comments actually if you're watching it in the YouTube, and feedbacks are also welcome. I guess no one is there in the meeting or thing, or everyone left. If any of you present and have doubt, you can put it in the chat box. Okay, so no one is there or no one message. So yeah, that's fine. We can close today's session. It is almost 8 o'clock. So we'll close today's session. If anyone is having any doubts, you can always put it in the comments in the YouTube. I'll respond to that. Thank you for attending today's session. We'll again meet it on next Tuesday at the same time from 6 to 8 p.m. Thank you guys. Yeah, thank you.